small crowd, but that's okay. I should have, you come up with these titles, you wonder whether, maybe I should have said wildly unsafe pointers for a chaotic world or something,
Make your pointers great again.
Exactly, make your pointers great again. So this talk is, a shorthand for it might be, let's say, Rust is cool. Can we prove interesting things about systems that use a pointer system analogous to Rust, ownership types, if you will? The background here is that we have relatively recently introduced this formal verification tool called SPARC 2014. SPARC, the original version of SPARC is probably almost 30 years old now, and it has always been, from a dynamic semantics point of view, a subset of Ada, but from a static semantics point of view, a much richer proof-oriented language. We're beginning to get some interest in SPARC in places that were not traditionally Ada users. So traditionally, Ada has been used in the aerospace and defense industry. I heard someone describe the industry he was in as the industry where things go boom. But he was actually talking about the chemical industry where things blow up. But I think you could also call the aerospace and defense industry places where things could go boom. And in commercial aerospace, hopefully it doesn't, but now and then it might. But we're finding, because of the focus on security these days, there's a growing interest in a language allowing you to actually prove things about your program, in particular proving that it's secure. And SPARC has emerged as one of the relatively few industrial strength formal verification systems. But as we also know, dynamic data structures are more easily represented using pointers. So the question is, SPARC, until this year, forced people to make creative use of arrays instead of any pointers. So you want to have a linked list? Well, you have an array with indices that have the next element identified, and you can do trees that way and all kinds of things, but that gets kind of old. And if you're trying to lower the entry barrier to use of formal methods, coming in and say, and oh, by the way, no pointers, is a little bit of a painful statement to make. And in particular, we've got a couple of new SPARC customers who have kind of said, we love this, but you got to give us some pointers. They can be simple, they don't need to do a whole lot, but we need a little bit of a pointer. So that's sort of what we're trying to do, is give you a little bit of a pointer and not lose the ability to prove that it's safe. How do you start proving things about pointers? And I would say these days the notion of separation logic is probably the most powerful approach, but it's also one that the average industrial programmer, and I don't mean that as pejorative, but I mean someone who actually has to deliver the code and has to fly or do appropriate useful stuff, drive, etc. It's not clear they're ready for that kind of a heavy annotation burden. So pointer ownership emerges as a viable alternative. It also is getting some serious traction through the language Rust. So that's what we decided to do, was to add to SPARC the ability to use pointers, but in a way where ownership is part of the model. SPARC itself, I don't know how many are familiar with it. Anybody ever use SPARC? Or, wow, 2 out of 10, that's pretty good. Get myself up. It's a multi-paradigm language, as is Ada, I suppose. Object-oriented. You can do some amount of functional programming. In fact, more and more these days, real-time programming and certainly multiprocessing. But it has a specification sublanguage built into it, which is kind of nice because a lot of these formal methods tools, you have to learn a new language to do the proofs. And sometimes the new language is with a set of new tools, and those new tools may limit what part of the real language you can use, what part of programming language you use, because it only supports some semi-random subset. That's sort of true in SPARC, but it's a very well-defined subset, and it uses SPARC 2014 uses the Ada front end as its parser, if you will. Whereas in the past, in the old version of SPARC, there was a completely separate tool suite and so on, and there might be little differences and so on. The current one is integrated tightly with the standard Ada front end, and so it's much more robust in that sense. Something that's being used by hundreds of thousands of people, not just a cadre of 10 people who care about formal methods. And the other thing is that because Ada is used for large real-time systems, SPARC, and many of those do have critical components. SPARC has kind of a ready-made user base who really care about its ability to work in the context of a larger system. So in terms of what are the restrictions relative to Ada, these days about the only restrictions are no exception handlers, because they're truly a nightmare from a proof point of view, and no reassignable pointers until this year. And I'm going to talk now about how we're adding. SPARC, as I said, is a commercial tool, and it can be compiled in conjunction with sort of regular Ada, C, C++. You have to always mark the SPARC code, say, okay, this code is to be further processed by these SPARC tools, and it can be a small piece. It can be like one function in a larger package. It can be a whole package. It could be a whole program, conceivably. The GNAT compiler compiles all of these languages to machine code. And when you identify SPARC mode, it does further checking just from a legality point of view. And then this other tool, GNAT prove, can be kicked in to do the formal verification. You don't have to. You can just say I want to stay within the SPARC subset of the language, and that the compiler will enforce that without any use of the proof tools. Or you can say, yeah, now let's try to prove that the thing actually does what I claim it does. And that's when GNAT prove comes in. So one of the things that's interesting is one of our largest SPARC customers is a company in Europe called Thales. And Thales does a lot of air traffic control and that sort of thing. And they really like SPARC, but they tell us, you guys don't know how to sell it, because you make it sound like this amazingly complex thing that only a company that it can afford to have 100 PhDs in computer science can use. And they claim that they've been able to get value out of it just because of some of the built-in features. And then when they decide to invest more heavily in a certain piece of the system because it's really critical, they can get more value. But the point is that you can actually start by just having some of these implicit things, no reads of uninitialized data, no runtime errors, no deadlocks, no data races, and so on. And that you get out of the box. If you write in SPARC, it does all those kind of checks. And then you can begin to say, well, but I have more things I want to say, and I'd like you to prove. And so things like information flow. I claim that this output from my function is dependent on the incoming values from only these two inputs. So you can actually claim certain things about the information flow, which might be relevant for security, or it might be just relevant to sort of say something a different way to be sure that you understand what it's doing. And SPARC will verify your information flow claims. You can also begin to put in pre and post conditions, and SPARC will again try to verify that the post condition is provable if you assume the preconditions. You can also use type invariants, various kinds of predicates, and so on. You can also, even if you have code that's not written in SPARC, you can decorate its interface with pre and post conditions, which will then be assumed to be provable, but then from the user's point of view, they can take advantage of those post conditions and will verify the preconditions. So somebody else will have to verify that whatever you wrote on that API was in fact represented the truth, or some approximation of the truth. But it allows you to integrate with components that you may not control, that you can't necessarily bring to the same level of proof. SPARC has two underlying technologies that allow it to do its job. The first one is pretty conventional control and data flow analysis, something that almost every static analysis tool does. And that's the kind of things that don't require annotations generally, correct initialization, no use of uninitialized data. That's a pretty well understood problem, and SPARC does that. This information flow properties, it verifies those using just information, control data flow. And then also the whole deadlock and data race detection stuff is done pretty much using that technology. And I wouldn't say it's anything particularly unusual. It's hopefully correct and well done, but otherwise pretty well done, understood. And then there are the things where you start getting into pre and post conditions, type invariants, properties of computations, such as range constraints and that sort of thing. And then you begin to get into the heavier duty proof capability. And the newer version of SPARC was completely rewritten to take advantage of SMT solvers. And it goes through an intermediate verification language called Y3. And that allows us to basically target almost any SMT solver out there. And as delivered, SPARC comes with Z3, CVC4, and alt ergo, and actually a fourth component, which is our own abstract interpretation tool called CodePeer, which is used for certain kinds of floating point range propagation, for what that's worth. But it turns out that good old abstract interpretation is better than SMT solvers at certain kinds of things. So the big thing that this customer, Thales, told us is you can progressively move up the chain. And you don't have to sort of start off at full specification of functional correctness and so on. And it can also just be used for some of the code. You can use it for most of the code or just little kernels and so on. And then their marketing department, our marketing department, I don't know who, came up with the good, different levels. There's the stone level and the bronze level, the silver level, gold, platinum, wow, this is getting great. The other point to make is that in terms of how much of your code is sort of just taking advantage of these value propositions, if you will, this is actually not unreasonable, and maybe it's probably still not to scale. This might be, most of the program, and then this is, a good third, and then this is maybe a tenth, and then a 1%, and down to the 0.1% there on the full functional correctness. People sometimes say, well, what do you mean full functional correctness? And my favorite example is someone says, okay, I'm going to write pre and post conditions for a sort function. Cool, and it's going to precondition. I don't care as long as it's just well-initialized array. Coming out, I'm going to write a really neat kind of loop that's going to say that, for I in 1 to n minus 1, a sub I is always less than or equal to a sub I plus 1. Cool, fully defined, right? Well, actually, no, because you got to also say that the output is a permutation of the input. And, that's, of course, it goes without saying, but actually it doesn't go without saying when it comes to proving things. So that's just an example of full functional correctness. You really are stating things that you normally would just not even think, why would I have to go that far? But when you start doing high security applications, cryptography, and so on, then the post conditions challenge the real code for length. I mean, they get pretty long, but they intend to be a functional representation, probably very poor performance representation of what the thing does. So that's an option. You can go that far. But it's like a ladder. You can sort of climb up and get to there. It's interesting to see that SPARC, in fact, has been used. These are different domains: security, air traffic control, and avionics. And usually these people have some kind of a standard where there's some funding agency or certification agency that says, well, yeah, that's all well and good, but you got to satisfy this standard. In the FAA, it's DO 178. DEFSTAN is a UK standard. These other ones, common criteria is the National Security Agency, and so GCHQ is like the NSA for the UK. And they have different levels. And it's usually when you get to the top level, like level A or SIL4 or one of these other things, that the agencies begin to get, no, we really want this to be right. And so people have begun to adopt SPARC. And more recently, interesting thing is it used to be the FAA said, formal verification is irrelevant from our perspective. If it's helpful for you, great, but we're not interested. We want to see tests, test. That's the only thing we believe. But in the most recent version of DO 178, they've admitted that formal verification is actually useful. And in fact, it can save money. Yeah.
Still got a way to go though, right? It's only in the appendix, really.
Well, it's a separate document, right? It's DO 33 something or other, 330 or 1 or one of those. But that's not like it's an appendix in the sense of only some people will accept it. It will be accepted, but it isn't in the main document because that was written beforehand. They didn't want to write the whole document, so they added these things on model-based development, on object-oriented programming, on tool qualification, and on formal methods. Those are the 4 additional documents. I don't know what they want to call them. Interesting thing is that even with this gang really trying to retrieve level A and so on, nobody made it up to full functional correctness. That's just like, you just don't generally go there, because that actually is easier to deal with from a testing point of view. You just want to know, did I get the right answer? Yeah, well, but will I always get the right answer? Then it's easier to sometimes do things with formal verification. So we see a number of customers trying to use both. That is, I want to do testing. That's a good thing, actually. I think testing is worth doing. But then if they want to really be confident about, well, does it really cover the whole input space? If somebody has a million monkeys typing on the input, can I be sure it'll never do something bad? That's where formal verification becomes very helpful. Anyway, the IFACS this is interesting. This is a major component of the UK air traffic control, fully written in SPARC. And, so, okay, pointer safety in a parallel world. What's the why bother? So these are the kinds of things that you'd like to be able to prove will never happen in your program if it's using pointers. And you know, the best is to put it in the type system if possible, but a lot of these really require flow analysis and propagating information across function boundaries and so on, meaning preconditions, postconditions, and so on. So proving pointer safety in a large componentized system is probably going to require a lot of the same tools that are used for proving anything formally. But these are the kinds of things we're trying to prove. No null pointers. Well, that's pretty obvious, and something that it's about as hard as proving no uninitialized data use. It's sort of a binary thing. Either it's, you don't have to kind of track individual values. Either it might be null or it won't be null, and that kind of thing. Ownership. So at this point, I should introduce the idea of ownership. And what ownership means essentially is that at critical points, at least, there's exactly one pointer to any piece of heap storage. Any storage that was allocated dynamically, at certain parts of its lifetime, this is the only pointer. And if I set that pointer to null, I can reclaim that storage. And so you try to be sure that you have proper ownership at appropriate critical points. It also means that when you set the pointer to null, you want reclamation to occur immediately. Or if it's already null, then presumably you've already reclaimed it or you've moved it or whatever. And furthermore, you don't want to make any accesses to things that have been freed. And that's why you want to get down to just one. You want to be sure there's not multiple pointers at the point when I free the object. So you want to be sure you dart down to a point where you know there's exactly one pointer, you can prove that there's exactly one pointer, and now I can safely reclaim the storage. Other thing that it turns out SPARC already had a lot of worries about aliasing, but without pointers, the major kind of aliasing you're talking about is parameter aliasing, either with two parameters where you have names for both of them in this function, and it's able to update one or the other, and it really doesn't want to have to worry about the possibility that if I update x, I might be changing y. I have two parameters, x and y. So parameter aliasing was disallowed in SPARC early on because you had real trouble proving much of anything if you had to worry about that possibility. And the other case of interest is global variables. You can't pass, in SPARC, unlike most languages, if you're going to use a global, you got to tell the compiler, I'm going to use that global. And if you don't tell the compiler I'm using it, you can't use it. So it's almost like another parameter. It's sort of it's an implicit parameter if you want to think about it that way. But part of the parameter profile, if you will, is I've got some global inputs or global input outputs. And in that sense, they're treated the same way as parameters from an aliasing point of view. If the code has visibility and is allowed to read or write a global, then you can't pass that same global as a parameter in a way that might. So no hidden aliasing. Surely you can have aliasing like, if you talk about the ith element of an array and the jth element of an array, well, those might be the same thing, but only if I equals j. That's not hidden from the compiler's point of view. It can do the analysis to decide whether I might equal j. But as far as two parameters, having to assume the worst is just bad news, and you don't want to have to do that because you really can't prove much if you assume the worst everywhere about aliasing. The other thing is, and it's sort of related to aliasing, but it also comes back importantly when you start talking about parallelism, is that you have at most one name that allows you to write an object, and then you must have no other names that allow you to do anything with it. Or you can have multiple names that allow you to read something, but then there shouldn't be any names out there which might allow you to change them. which is essentially the same rule I was describing before in terms of aliasing. But it begins to think of it in terms now of that makes sense for parallelism. So the ownership-based approach is an alternative separation logic. It happens to be quite amenable to deductive proof because the properties you're trying to prove are the kind of thing that you can generally include in a precondition, postcondition, and so on. It supports this concurrent read exclusive right model. Either you have full ownership, which means you have the exclusive right to read and write this thing, or you can have partial or shared ownership where multiple people do it. And as I mentioned, SPARC already had these anti-aliasing rules. If the pointers obey the same anti-aliasing rules, that is, you can't pass a pointer to an object if it has any other way to get to it, either any other pointer or direct reference and so on. There's actually a long history. I think Rust is in some sense, the thing that's made ownership suddenly hot. Hermes is a language that's been around for a long, well, I'm not sure it's still around, but it was invented a long time ago, originally called nil, and then I think the marketing department got involved at IBM and said, let's call this something other than nil. This was, I think, David Strom's language, where type state was originated. This was the mother of type state, which certainly has lived on. But Hermes was a language that had this, what they called it, a handoff semantics. Once you pass an object, you don't have it anymore. And that's kind of the same idea. That's sort of the underlying model of this full ownership. When you pass a parameter, you give it up. You don't have it until it essentially comes back to you. Okay, I threw in Parasail there. That's my own little favorite language. And La Casa is a relatively recent language. I think it's builds on top of Scala. Alias Java is Jonathan Holder's there. Just naming those, critical people. I thought I'd just make a quickie here on reference versus pointer. Terminology is sort of a pain, and ownership is sometimes called unique pointers or owning pointers or other things, and sometimes object ownership versus pointer ownership. I think the term reference and pointer are also used sometimes interchangeably. I tend to like this sort of a notion that a reference, it generally is always an alias, and it generally refers to the same object throughout its life. So it's not something that it's not reassignable. That's an unusual notion of a reference. And if you use a reference on the left-hand side of an assignment, you're assigning to the thing that it refers to. You're not changing the value of the reference, you're actually changing the thing it refers to. With a pointer, if you have a pointer on the left-hand side of an assignment, you're generally changing where the pointer points. And that's something that you're expected to do during the life of a pointer. So SPARC has references in the sense that parameters are passed by reference and things like that. And there are anti-aliasing rules associated with that. When you start talking about assignable pointers and reassignable pointers, to avoid aliasing, you need these safe pointer rules, which limit how many different pointers can point to the same place and so on. So challenges with pointer ownership. One is from a usability point of view, pointer ownership supports tree-ish data structures only because it's very hard to create a loop, a cyclic structure if you have ownership because you end up having implicitly two owners. There's of the root. You've got the thing pointing at the root, and then you've got the tail pointing at the root. So that's going to be a problem. Or bidirectional link, doubly linkless also is a problem. But there are a lot of structures that you can do this way: trees, linked lists, vectors, hash tables, maps, all kinds of things. So here we rationalize this. Well, it's okay because you can represent these in other ways. Of course, you could represent these using arrays as well. But here, I would argue that once you've got once you can create trees and linked lists and so on as elements of an array can become a pretty powerful structure. So you could represent a graph as a vector of nodes, where the nodes themselves could be lists of things and so on, like lists of predecessors, lists of successors, and so on. You don't need to have truly cyclic data structures to represent graphs. And in fact, in my experience, you find a good graph package that often doesn't use pointers for the links between the nodes because the node may exist with having no pointers to it. So pointers would be kind of an awkward approach. You sort of need someplace where it lives independent of pointers to it. So that's, I would say, rationalization. I don't hear people from the Rust world say, "Oh, I'm struggling with these, doubly linked lists." It's just there are other ways to do things. So, but the other thing is that you do want to be able to walk you want to be able to walk a data structure, its ownership. But that implies you've got some kind of a walker that is giving you access to that tree, but doesn't sort of count, or it's a secondary reference of some sort. And we, in our work, have used two terms, and borrowing is something that the same term is used in Rust. We talk about observers and borrowers. An observer is a sort of a secondary reference that lets you read an object only, and a borrower lets you update it. And there should never be more than one borrower in existence at a time that's actually usable. And when you borrow from the main pointer, whatever, the owning pointer to the object, that owning pointer becomes unusable until the borrower goes away. So these are some of the notions, and then there are a series of rules, which I guess I'll get to in a second. The other thing that is a challenge, and actually someone came up to me earlier today and was talking about this and said, well, how do you do this in an existing language? Well, SPARC didn't have pointers, so adding ownership is not a big problem. But SPARC is defined as a subset of Ada semantics, dynamic semantics, that is, you can use a regular Ada compiler. So you do have to deal with the fact that you're trying to take an existing language which has pretty much free use of pointers and trying to come up with a subset of that, a well-defined subset that has ownership. And newer versions of Ada allows you to very easily put additional annotations on data types. So you can say this is an owning type, an owning access type, an owning pointer type, and then the rules could apply to that. But you might have other pointer types that are, well, willy-nilly, anything goes kind of thing. Ada already has some restrictions, but they are more at a sort of a lexical level kind of thing, which is not very useful. And the only way to reclaim an object in Ada is to call this thing called unchecked deallocation. It's a big, long word, oh my God, I guess I'm really asking for it because it's not checking. Whereas one of the goals here is so that anytime you do deallocation, you know this is the only pointer because of all the other rules that have been enforced. Garbage collection is allowed in Ada, but the only implementations of Ada that do it are those that are built on top of a virtual machine, like there's an Ada version that runs on top of JVM, there's one that runs on top of C# VM, and those have garbage collectors, but it's a pain in the neck if you're also trying to do hard real-time stuff, and Ada data structures are pretty complex. So anyway, this is an alternative that doesn't require garbage collection because it's synchronous. You know when you get rid of the last pointer, you can immediately reclaim the storage, which makes people doing real-time systems much happier because real-time garbage collection is one of those things that is not fully trusted in the high integrity world, I would say at this point. The other thing that every time you start talking about ownership, you need to distinguish between moving and copying. Moving is where you take the object or the reference to an object and you move it into a new place, and the old one effectively goes away. In Rust, the semantics, they do use assignment for that, which I think is debatable because all of us sort of know what assignment does, and it usually doesn't have any effect on the right-hand side. But in Rust, when you do this, this object effectively becomes unusable. It's sort of poisoned. You can't touch it until you assign something new into it, or until you sort of this goes away. What we're talking about doing in Ada is actually nulling it out. That is, as a side effect of this, we would actually null the pointer out. In SPARC, what we're doing is we are pretending we null it out. We don't actually null it out, but we, from the proof point of view, it is nulled out. Which means if you try to use it, it's going to say, sorry, it's null, even though we'd actually didn't do anything. We didn't actually physically change it. So it's sort of more like the Rust model. Or you can explicitly set it to null, which does set it to null. The other thing is providing some way to do a deep copy. One of the nice things about ownership is the definition of what a deep copy is automatic. There's no real question. If you have an owning pointer, you always would copy the thing it points at. There would never be a time when that would be a debate. So you can easily add a feature into the language that does deep copy. And there are a lot of things you can do, like streaming and all kinds of things that once you have this notion of ownership, become a lot simpler. some languages, there are additional annotations to help you do streaming and so on, to imply that this owns that and so on. Here, you're using ownership from the beginning, and these other operations like streaming and copying and so on become straightforward. And then you need some syntax for creating these temporary transfers. This is a full and final transfer of control. This is making a copy, and we also want ways to create temporary references, either something that gives you full access or only giving you read-only access. This happens to be Ada syntax, not my favorite, but it's an existing feature in the language, so we're sort of just piggybacking on it as a way to create a read-only reference or a read-write reference to the same thing. But now, again, that right-hand side is effectively being poisoned. As long as this borrower exists, that right-hand side cannot be used for anything else. Similarly, as long as this observer exists, that right-hand side is itself also only an observer. You can't read or write through it. As far as rules go, I'm not expecting you to read this line here, because if you can, then you probably should be doing something else, like flying a jet or something. But there are rules that are not too surprising about what must be true about these objects. For example, you can't borrow them if they've already been borrowed. You can't observe them if there's a borrower out there. So there are lots of rules that determine whether you can do these things, and they will allow you to preserve these properties that you never have, for example, more than one way to update an object. And if you do have a way to update it, you don't have any ways to read it, any aliases. So, read these at your will. The notion of a handoff, I find a useful way to think about borrowing, as I mentioned earlier. But that's the idea, is you're handing off something for someone and they have the baton until they give it back. But as long as they have the baton, they are in charge and can do what they want with the object. So this is another eye chart, unfortunately. But this is a relatively simple pointer program that's trying to walk a linked list, find the last two elements, and reverse them. I have no idea why, but let's presume that it's doing that. So if we just stare at this for a little while, we start asking our questions like, are there any storage leaks? Are there any dangling references? Does the net effect of this create dangling references, make any null pointer derefs? Do we create a circular linked list? We're supposed to have a singly, uncircular link. Does it produce the right answer? Those are all interesting things, and they can all be specified to some extent, but many of those are now going to be implicit in the rules of borrowing and ownership and so on. In fact, these top four are now going to be automatically true. And all that you need to worry about is if you get the correct answer, and you can use testing to do that if you want, at least for some subset of the possible inputs. So how do all these rules help? Well, one of the things I didn't emphasize, but we use the lifetime of a secondary reference, of an observer or a borrower, to determine when the original object, for example, here we have X, which is referring to a linked list, let's say, coming in here. X is a linked list pointer. And as I said, once a borrower or an observer exists, then X itself is no longer can be used for whatever you want to do with it. So in Rust, I don't know if you were at Nico's talk earlier, but in Rust, the compiler actually looks forward to see when is your last use of something like this borrower, and then after the last use, you can now go back and start using X. We chose to have a somewhat simpler model that as long as this object exists, which in Ada goes from this declare down to the matching end here, then it prevents X from being used in a way that conflicts with the walker. Here in this case, this walker is giving full access to the object referenced by X. So quickly looking at it, so if X is null or X.next is null, then we have less than two elements, nothing to do. If X.next is null, then we have exactly two elements, and this does a swap. The compiler will catch if we don't actually do a swap, or we create some kind of a circular linked list or something. And then so we're walking down the tree, and we're now going to do a little subsection here. And here we're creating another reference, if you will, something that also allows us to walk. And it is borrowing from the earlier borrower. So this borrower now is no longer usable for purposes of updating and so on. All the updates now have to be done through this next pointer. So we've got a nested set of references here. And here, this is the critical thing. What makes something useful to walk a data structure is you need to be able to set it to something else. If you can only set it to the root, that's not really very useful for walking. So here we are, in fact, walking down this linked list. And the question is, what are the protections there? Could we, here we initialize this thing to point to the root of this linked list. Are there any restrictions about how we can change this walker once it's been created? And the rule is that you can set a walker to point to anything below it. So if you got a tree, you can set it to point to any sub-element of the tree, linked list, anything later in the linked list, hash table, anything maybe later in the hash table or down below. So basically, you can't actually go up though, so that's sort of an issue. But we still got to hold on to our original pointer. But it does allow you to essentially walk down a data structure. And you can hold on to values by just, walker here is preserved. We create a new thing called next pointer, which then walks its way, down the next level. And then we can start using walker again once this inner borrower goes away. I did mark the places where we're doing moves, and moves are where this thing effectively becomes poison or gets nulled out as a side effect of the operation. And here we're actually moving the primary ownership from the next field. So this is a linked list, so every element in the link has a next field. And we're taking the pointer out of that next field and we're moving it into this local pointer. Here we're doing another move. Here we're moving a null into that pointer. Here we're moving the root into the next pointer of this second value here. And then finally we're setting the root back to the second. So this is just doing a swap, but it's doing it kind of carefully in a way that ensures there's never more than one access to a given object that you can actually use. So effectively that goes null during this period. And in fact, here we set it to null, but that's not really necessary. It's effectively null as well already then. And then we do this swap, which sets now x to null, and then we effectively do this last thing, which effectively sets this second to null. So by the time we're all done, second is back to null, x is back to a non-null value, and everything has been swapped. Any questions about how that all comes together?
So you're basically laying move semantics over the existing semantics of Ada, so it's still a subset technically. Is that roughly what's going on?
Yeah, I mean, we're still debating this. For SPARC, they really wanted to get this going right away, and they didn't want to change the Ada semantics at all, which means that's why it's not actually nulling out the pointer. It's just pretending it nulled out the pointer.
Yeah.
It's also, in our proposal for Ada, again, we haven't completely finalized it, if at this point x has a non-null value and you assign something new to it, it will automatically reclaim that value. So the left-hand side of an assignment gets reclaimed if it has a non-null value and it's part of a move. SPARC, again, didn't want to do that because they felt that would mean changing the underlying Ada semantics without having, Ada isn't there yet. In some sense, it's following behind SPARC in terms of language change. So they require that before you do this, x has either been effectively nulled out by being moved, or you've explicitly deallocated the space it points at. So you will do explicit deallocations, but they will be provably safe. And you'll have to do them before you leave a scope. So in SPARC, it'll be more explicit. In Ada, the intent is that the deallocation becomes implicit. But the SPARC guys like to see things, they don't like any implicit semantics behind the scenes. So it actually works out pretty well for them. This is a very trivial example of how this is being integrated into the SPARC IDE. The SPARC IDE, basically, it's It's the same one we use for the compiler and our other static analysis tools and so on, but it has the notion of you run the tool and then it either gives you green, saying everything is good, or you can see oranges and reds and so on, depending on how bad the situation is. This one was trivial. It was just proving that these were safe and that y dot all equaled x dot all and so on. So it generates a bunch of messages. You can reduce the verbosity if you want to. I was madly this past hour trying to get a more interesting example going, and I found it. Forget it. They can imagine how interesting examples could look. And then this is a potentially slightly more interesting thing here. We're trying to insert a key or a mapping into a hashed set. I'm sorry, insert a new key into a hash set. And here we're creating a new object. And so you need to include that into your picture. I had showed it creating any new objects before. They were just moving existing objects around. So here, it makes perfect sense to create this object in this temporary right-hand side and then move it into the left-hand side. And this thing is now irrelevant and effectively unusable afterwards. And then we have here, this is, it does some observing here to try to find where to insert the new key into this hashed set. So this is doing a loop, and it's walking around. And here we have one of these observers as opposed to a borrower. And then down here, once we figured out exactly where we want to do it, we move the new object into the slot. And there's actually two moves going on here in that we're creating a new node here, which is effectively taking the value of the old node and moving it into this newly created node that's going to be in our hash set. And then we are moving this newly created node into the old slot. So there are actually two moves going on inside that one statement. And then again, the questions are the same, and the claim is that when we're all done, we can be certain that these four have been eliminated at compile time, and you're stuck still having to test that one. And conceivably with SPARC, you could have additional pre- and post conditions that would give you a better sense of whether this is also happening. But with these four, you don't do anything. It's part of the semantics of the... So in terms of how this relates to parallelism, given that we have these anti-aliasing rules, you must not pass a writable global as a by-reference parameter, so you can't, as I said before, if something has access to a global variable as per its declaration in SPARC, then you can't pass a reference to it as well as a parameter. You can't pass the same object twice if either one has read-write access. Pointer ownership rules also, as we know, ensures that you only have one writer access or a single read-write access. And then the data erase prevention is basically that when you, threads can be treated essentially the same way as function calls in terms of ownership, and you get the same data erase prevention by simply knowing that there's exactly one read-write pointer in existence at any time. So this is my provably safe pointers are practical. Okay. And I think we're seeing that our customers want to use SPARC, do want to use pointer-based structures, but pointer ownership seems adequate for their needs. They don't need to create cyclic data structures and so on, which they actually wouldn't like to have anyway, because they're always looking for things that they know about the properties in terms of performance and so on, and cyclic structures are always a little scary. They don't like recursion either, but they're willing to think about recursion, but cyclic stuff is really scary. And our sense is that separation logic would not be something they could deal with. And that's kind of a side effect of this ownership model. Parallelism safety checks are very straightforward. Okay, any comments, questions? Nico?
I have a question, actually. I came a little bit late, maybe I missed it, but if you go back a few slides to the observer example, that one, how do you know that this pointer is an observer? Is it because it says access constant node in its declaration? What makes that an observer versus a borrower?
Yes. when you take an owning pointer and you use it to initialize a access to constant pointer, then it is treated as an observer, and the original pointer also becomes an observer itself. It becomes read-only. The question was, I'm supposed to repeat the question, how do you know when you're initializing an observer? And the answer is, it's this particular syntax, which pre-existed this whole effort. Ada already had this notion of kind of an anonymous access to constant, and we essentially hijacked it to say, in this, when you're doing ownership, we're going to treat that as an observer. Normal Ada wouldn't put any restrictions on that. It would just be, well, you've now got yet another pointer. But here, we're treating it that way. Other questions? That is obviously the delicate part here, is that we have an existing language, and so we're trying to take advantage of the existing features of the language without having to add a whole lot of new syntax and so on. It might be nice to have a somewhat clearer syntax, but presumption, if these are the only pointers you're using, well then, this is a reasonable interpretation. Yes?
Has there been any work on proving the soundness of the Ada memory model, or more specifically this memory model?
Has there been any work on proving the soundness of this memory model? Well, define soundness in this sense. I think we feel comfortable in our ability to prove that our rules ensure there's at most one pointer at certain points in the lifetime, such as when you deallocate it, or when you use it for changing something. So we feel comfortable with that. I'm not certain whether you want to go the full memory model. Has that kind of scary sound about it, and that I wouldn't want to get into the battles with some of the folks out there with the weak memory models and so on. This is a pretty simple model. Yes, John?
One of your early slides, you had Parasail up there as an example of this sort of approach, but my memory is that was more of a call stack-based region system, not ownership.
It has both. You can use regions in conjunction with ownership. To some extent, Cyclone and some of those languages had some aspect of ownership. It was more that the object was owned by a region as opposed to being owned by a pointer. It was a little different. But Parasail happens to use region-based storage management.
Discipline, though, of regions, right?
Right, but the actual references to those objects follow ownership rules. They have a handoff semantics. When you pass an object, you give the caller read-write access. You give away all access while they exist, and then when they're done, you get it back. So it uses an ownership model, but it's object ownership in some sense, since there are no explicit pointers. But you do have pass by reference, so effectively pass by reference, as we know under the covers, is passing the address of the object, and that is treated as now that's the owning pointer, if you will, or the borrower during the existence of the call.
So my question then is that was regions, did you consider regions here for this initiative, or because not using it because either it wasn't compatible, or just because you think straight ownership types are enough and better?
I think regions are extremely valuable, and I think it's sort of a stepwise approach here. Ada has some notion of heaps, subheaps, but they're not very useful because they're based on the type as opposed to on the object. You really want regions associated with objects, and in Ada they're associated with the types of the pointer, which doesn't really work. I don't know whether Rust does anything with regions-based storage.
Region-based, no, but you can model it in a library.
Yeah, so in Parasail, all objects are by default allocated in a region that's local to the procedure they're within, and that region as a whole is released when you exit the region. But you can also reclaim bits of it in the middle. So it's just a way of reclaiming storage efficiently when you leave. And the other thing that's nice about regions is you get better locality of reference. So particularly if you've got a multi-threaded program, you would like, if one thread is over here creating a complicated data structure, another one's creating a complicated data structure, if they're using global region, then those structures are all going to be interleaved. Whereas if they have local regions, then they each are allocating within their own regions. it's really a separate thing. It turns out to be much easier to implement once you have ownership. So I do kind of hope that we will get there, but right now we're trying to just get the ownership going.
Thank you.
Yeah. Other questions? Yes?
When can we expect to see this in Ada or SPARC?
It's now, I think the latest version will have it, but if not the latest version, then sometime in the next 6 months it will be the version you get if you download the latest thing.
Okay.
So it's, yeah, we have some very important customers who are knocking hard on the door with money in hand, which is usually the best way to know that things will happen in a timely fashion. It's going to be very exciting. We're announcing this, I would say, the next few months. This extremely big company that's very hot these days, and they're building a secure kernel with Rust. No, actually with SPARC. And they really want to have pointers, these kind of ownership pointers. Any other questions? Okay, thank you very much for coming.